Hi everyone, I'm Rachel Pad, and Scott and I are interviewing Miss Akers, one of the physics teachers here at Andover. She also is a biology teacher, and so we thought she would be the perfect person to interview about chemistry and cooking. So we're going to ask her some questions. Okay, our first question for you is, what are some ways chemistry is incorporated with cooking? Feel free to elaborate a little bit.
Well, as soon as you put two food ingredients together, you have a solution or a mixture. So that's chemistry right there. You have molecules in there that are interacting. So, or just frying an egg, you've got egg and heat. As soon as you add heat or take heat away, make it cold, you've got another chemical reaction going on.
How do thickening agents interact with other ingredients on a molecular level? In class, we've talked about making white sauces and stuff, and I know when you add flour and the butter and the heat and stuff, something happens on a molecular level. Can you explain that for us?
Okay. Well, again, it boils down to heat and the reaction on protein. So when proteins are heated, they relax. It's called denaturing the protein. And so it's going to stretch out and relax. So in a baked product, the relaxing is going to go this way. But when you make use it as a thickening agent, it's going to relax, and then the amino acids will bind that fat with the water or the milk or the chicken broth, and then it will start thickening it up, binding it together.
Why do sauces begin to thicken once brought to their boiling point without, like, the flour? Or
well, you have to have some protein.
oh, really?
There.
Okay.
Yeah, it'll either be in the cornstarch. Okay, so you have your polysaccharide there, and that's a huge starch molecule. So that will bind, or flour. One of those two. Arrowroot is another product. I don't know if people are familiar with that.
I've heard of that.
But that's also a polysaccharide. So that heat is what is going to open up the protein molecule, and then the amino acids within that will be hydrophobic, hydrophilic, and they will bind the fat that you have and the liquid that you have together. And then that boiling point is what completely relaxes that protein and then starts to thicken.
Oh, and so with the different polarities in, like, salad dressing, you were kind of talking about hydrophobic and
hydrophilic.
Hydrophilic.
Right.
Can you explain that a little bit? Because I know a lot of people wonder, how do you mix a salad dressing with vinegar and oil?
Right, because they don't mix.
Right, because of polarities.
Right, and again, that some salad dressings will remain separate, and you just shake them temporarily. They'll be somewhat mixed. But if you want it to last, like a mayonnaise, like a ranch dressing, there's fat and water in there, but you have to have another ingredient that will hold them together, and that's called an emulsifier. So the emulsifier is, let's say, an egg. It will bind the fat, which is either an oil or it could be just the yolk of the egg, with the liquid that's in it. And again, it's that protein that will do its thing to bind the other two ingredients together.
Very cool, thank you. So, thank you so much. I think that's all the questions we have for you.
Okay.
And so, next up, we're going to talk to Mr. Beauchamp about chemistry and ceramics.
Okay, this is Mr. Beauchamp, and I'm Scott, and I'm asking him a few questions about how ceramics is affected and related to chemistry. How does ceramics factor into chemistry?
Well, ceramics is all about chemistry, really, if you think about it. We deal with materials from the earth, and basically about 95% of the Earth's crust can be used in ceramics in some way or another. So it's very important for us to have a working knowledge of chemistry and to use chemistry when we make stuff.
Go ahead.
Many of the ingredients, as you can see over here, we use those when we mix glazes, and clays are about chemicals being mixed together, and by mixing together different ingredients you can get different properties from the glazes. So there are recipes online, and people have done a lot of research. You can come up with even your own recipes.
Okay, how do the molecules in the clay change after the piece has been fired and going through the different like stages of firing?
Well, clay is made up of, and people didn't really know what clay was made of until they had electron microscopes. And they could see that clay is actually made out of discs of silica that were held together with water, alumina and silica. And they're so microscopic they're hard to see, and that gives it its pliable properties. As it dries, it releases some of that water, and consequently it shrinks, but it holds its shape. When we put it in a kiln, basically what we're doing is we are liberating the molecular water and firing it and turning it basically back into stone, because clay takes hundreds of thousands to even millions of years of erosion to be made. Things that used to be a mountain or rocks before are clay now. And so basically what it does is it liberates the water, you bake the water out of it, it turns it back into stone. And that's the only way that you could recycle it, is through erosion for a long time after that. What happens though when you're firing at higher temperatures is that it will actually go through a phase where it goes through what's called vitrification, which means that basically it forms like a glassy cohesive surface. What will happen is at that point the clay is fired, even if it doesn't have glaze, it will hold water, and basically it will be turned back into like a really heavy type of stone. We use glazes for beauty purposes and for functionality, and when we put those on and fire again, they can have further effects on how it works. So sometimes some of those will be used for decorative purposes, sometimes for functional purposes. So there's a wide variety of characteristics that you can achieve by if it's fired really at a high temperature with certain types of glazes, or low temperature. They all have their own specific niche.
What kind of metals are used in glazes, and how does it affect the color?
Right. Our knowledge of those type of things is most important. That's what gives a glaze its color. When we look at glazes, some of the ingredients, when you mix them together, they'll be glass forming agents, meaning they wouldn't have a color. They'd be maybe like clear, and they would just seal it. So for a functional standpoint, that would work. But the additions of other minerals will add certain properties. The type of metals in science, they would call them transitional metals. And they are, we call them oxides. So art students will call them oxides. And they are things such as, for example, I've got one here. This is cobalt oxide. And when it's viewed in the container, it's a deep jet black color, but only small additions of it, when they're added to a pot or brushed on top, will result in a very bright ultramarine blue color. And so that's an example of one of the most very visible versions of that, very dramatic. Other types of things, for example, this is a pot that it's got clay, and they rubbed what's called red iron oxide on it. You might know it as rust. That's its common name. This glaze has a very peculiar look and feel, and these running things that are coming down here is from a mineral called rutile. Rutile is titanium, but it's impure. It's got iron oxide in it too. And if you look closely at these little wiggles, these are the titanium crystals lining up and forming iridescent type of things. And so this is a property of using rutile in a glaze. So all of these have different effects. For example, this isn't really technically this color, this bronze color that you see right here, that's technically not really a glaze. That's actually just oxides that were mixed on there, and that's a mixture of manganese dioxide with a little bit of nickel oxide. And when that's applied really thick, it actually looks kind of gold. So all of these things, depending on whether they're fired in an oxidation state or a reduction state, different things will occur. So for example, when we say oxidation state, we're talking about electric kilns, reduction, gas kilns. And so from science, you probably know that reduction means an abundance of carbon and a lack of oxygen. And so some materials, such as this is copper oxide that's mixed into this raku glaze. It is a reduction fire. We fire it with a lot of smoke, and the copper turns red. But if it was fired in oxidation, most likely it would have greenish tones. So we can use that knowledge of how we fire things to get different effects in what we mix.
Well, thank you very much. I appreciate
Oh, you're welcome. Yeah, science is very important in clay, so we know a lot about it, and we can use that to our knowledge.